Right, so question 4. We've got a vertical straight wire carrying an upward current of 24 amperes, and it exerts an attractive force per unit length of 8.8 times 10 to the minus 4 newtons per meter on a second parallel wire 7 centimeters away. What current flows in the second wire and in which direction? In which direction we can immediately answer. If you've got two parallel wires, then they'll attract each other or they'll have attractive forces on each other if both have a current in the same direction. So if both currents in the same direction, there's an attractive force between them. If the currents in opposite directions, there is a repelling force between them, as we explained in class. Right. So what is the formula that governs this? It is the following. The force between two wires carrying a current is, let me just get the brightness right, 1 second. Okay, so it is this mu0, this permeability constant, 2 pi times current in the one wire times current in the other wire, I2, over the distance between them times the length of wire. Okay, but how do we proceed now? What do we have in this? We know that the one current is 24 amperes. So let's indicate. Let's make a little sketch. You know, a sketch always helps us think. So here I've got my one wire, and I've got my other wire. The distance d apart, and the one current is, let's say, that one, I1, which is 24 amperes. And I know I2 is also going to be upwards because there's an attractive force between the two wires, which happens if they both currents are in the same directions. Okay, so I've got one of the currents, I've got the distance, these are just constants, so what do I not have? I'm missing F, I'm missing L, and I2 is what I'm after. Right. Okay, but what do they give us? They don't give us the force directly, they give us a force per unit length. They give us newtons per meter, force per length. So that is going to be F over L. Let me put the L on the other side. So the force equal to this, but the force per length is F over L. Is this newtons per meter. And this is the constant that they give us. This 8.8 times 10 to the minus 4 newtons per meter. That newtons per meter is what reveals to me that it's a force per unit length. That's this much. If the force is 20 newtons and the length is 10 meters, then it would be 20 over 10 2 newtons per meter. Okay. Alright, so what am I actually after? I'm after I2. So now let's get I2 by itself. Now we just have to keep track of everything. So it's F over L times 2 pi mu0 and times d over I1. Okay. Right. Okay, now we just substitute for everything. F over L, that is now the, what is 8.8? 8.8 times 10 to the minus 4 newtons per meter. 2 pi over 1 over, yeah, this is 1 over 2 times 10 to the minus 7, yes, Tesla meters per ampere, right? Because mu0 is 4 pi times 10 to the minus 7, so the 2 pi cancels with 4 pi, left with just 2, times the distance is what again? 7 centimeters, 7.0 centimeters, so that's 0.070 meters. And the current is 24 amperes, 24 amperes. So I'm multiplying, dividing, and the least amount of significant figures is, we have, it's 2, 2, 2, 2, this doesn't feature, that's exactly 2. So I'm going to provide my answer to 2 significant figures. Alright, so now it is just a matter of calculating these things. Let's just quickly calculate it. So 8.8 divided by 2 multiplied by 0.07 divided by 24 times 10 to the power minus 4 plus 7. Okay. So that's 12.8 amperes, so approximately 13 amperes. Two significant figures in my answer. Okay. Okay, so I want to say that it's upwards, but let's motivate it. So let's say because the force is attractive, both currents are in the same direction. Inch I2 is equal to 30 ampere, and the direction of I2 is also upwards. Okay, I think that is, let's just check, yeah, that is perfectly fine, right, okay. So, question 5 is just a simple application of a formula. We've got a solenoid with a current in it. Okay, so if you have a solenoid and a current in it, that means produce a magnetic field. The more turns of that the solenoid has per unit length, the stronger the magnetic field. So that means, yeah, the more turns, the stronger magnetic field. Alright, so where's the formula that we have that we listed in class? It's simply this formula. The magnetic field inside solenoid, its strength is given by this mu0 I current times N over L, right? N over L. How long the solenoid is, or the stretch of solenoid looking at how long it is, and divide that into amount of turns. So this will be turns per meter, in other words. So the more densely packed the windings or turns are on the solenoid, the stronger the magnetic field. Okay, so now it's just simply a case of substitution. Oh right, no, let's not get ahead of ourselves. And it asks for the magnetic field strength. We given the magnetic field strength, and it's asked how much current should it carry if it's got that many turns of the wire. Right, okay, so we're actually after I. So I is, in other words, PL over mu0n. And now it's just a simple case of substitution. 0.85 Tesla, 0.300 meters. We just substitute everything they give us. 30 centimeters, yeah, that's correct. mu0, this is 4 pi times 10 to the minus 7 Tesla meters per ampere. And the amount of turns that's dimensionless, that's just 975. Okay, and we just calculate that, and that'll give us amperes. You're going to check at the units. All that's left when they cancel is amperes as well. Which is why it's a good idea here and there and everywhere to include the units in your steps, because if you accidentally use the formula incorrectly, then you can see that you can sometimes see that in that the units don't cancel the way they were supposed to. So you know your answer should, let's say, be amperes, but the way that units cancels, as you wrote them down, it doesn't leave you with amperes. So why is that? Let's look again. Oh, I used the formula incorrectly, or this unit should have been on top and that one on bottom, or whatever. So including the units is a nice way to prevent yourself from making a mistake. Okay, let's divide by 975, divide by 4. I suppose I could, no, what on earth? No. No, divide by 4 pi, okay. Times 10 to the 7. Right. Okay, so how many significant figures we will write? 3. Okay, so 94.3 amperes. Right, and sure, that's quite a current. It's a very big current. But anyway, okay. Okay, so that's it for question 4 and 5.